Hello, we start, and first section today is about necessary condition 7.1, necessary condition. For Riemann integrability. It contains only one theorem, theorem 1. If f is integrable on AB, then f is bounded. Proof. By contradiction. By contradiction. So we suppose of contrary. Suppose f is unbounded. Let's say, for the sake of definiteness, we can suppose it is unbounded above. And proof is practically the same for unbounded below. Then what we should prove? We should prove that f is not integrable. F is not integrable. And it means there is no limit of integral sums. So what means no limit of integral sums? Let me recall. I is limit of integral sums, is a limit of integral sums, means that for arbitrary epsilon greater than 0, there exists delta greater than 0, such that for all partitions P with norm less than delta, and for all distinguished points psi I in related intervals, we have the following inequality for integral sums. That is the definition of the limit of integral sums. For arbitrary epsilon, there is delta, such that for arbitrary partition with small norm and for arbitrary set of distinguished points on intervals of our partition, we have the following inequality. Now, we need to prove that f is not integrable. It means such I doesn't exist. So, for arbitrary I real, f is not integrable. What it means? F is not integrable. is equivalent to that one. For arbitrary real number I, opposite assertion is valid. So it means we take opposite quantifiers. There exists epsilon greater than 0, such that for arbitrary delta greater than 0, there exists a partition with norm less than delta, and there exists a collection of distinguished points such that opposite inequality holds. And I'll do slightly more. So we need to prove that integral sums will differ from arbitrary given real number greater than epsilon, more than in epsilon, right? So how to prove it? Instead of that, I'll prove that we can choose integral sums arbitrarily large. If the sum is arbitrarily large, then it will be more distant from I than arbitrary epsilon. In fact, we don't need arbitrary epsilon, just there exists epsilon. But so what I want to prove even more. I'll take arbitrary partition with norm less than delta and consider the related integral sum. That is a sum of this kind. So we take values at distinguished points times lengths of the related intervals. Integral sums are written here, right? Now, remember what is partition. A, x0, less x1, so on, less xn equals to b. Once again, I take arbitrary partition. Arbitrary partition. But in fact, I need to prove only for some partition. I'll prove it even more for arbitrary. That is good for us. What's important? So I take arbitrary partition and then I look at points, right? And we have finitely many intervals. So union of intervals xi minus 1 xi is equal to our interval AB. And we know that our function f is unbounded above on this interval AB. F is unbounded on the whole interval, unbounded above, right? So it grows somewhere very large, somewhere. We have finitely many intervals, right? Then for sure, at least for one interval, for one of them, the function f grows arbitrarily large on this interval, right? So f is unbounded on at least one of those intervals, right? Because if it would be bounded above on each of those intervals, it would be bounded above on the whole interval, right? If it is bounded above on each of them, then it is bounded above on the union, right? but it is not bounded above. Hence, there exists at least one interval where the function is not bounded, is unbounded, right? It grows somewhere. So, okay, let me fix. So, there exists k, 1 less or equal k less or equal than n, such that f is unbounded above on xk minus 1 xk. Now I want to use a notation. So denote as tilde f p psi to be the sum of all other terms. So sum for I from 1 to n, but I not equals to k. So all other terms are considered. Psi I delta x I. So this S tilde consists of all other terms. So now look, once again, what happens? I took arbitrary partition. Let it be for arbitrary delta, so just the only restriction, the norm of that partition should be less than delta. So I take arbitrary delta, take arbitrary partition with this norm. So it means every interval is sufficiently small, right? Every interval. Then, now it's a little bit strange. So you see, in general, I should take arbitrary here, arbitrary set of distinguished points, right? To prove our theorem, I need to choose a system of distinguished points, right? Now, look, I don't care about psi I with numbers from 1 to n except for k. I don't care about other psi I. So all those psi I with other numbers I not equals to k, again maybe arbitrary. I don't care about them, right? But look, for psi k, the only thing which is important for us is this psi k. Why it is important? Psi k is a point on our interval, right? And this point we can choose as we want, because I want to prove the existence of such psi. So I choose psi k in a very specific way. How? Look, what I know about the function f. F is unbounded on xk minus 1 xk, right? So it means we can find as large values of f as we want. Extremely large values, right? And we choose a point psi k such that f of psi k is very large as we want, right? For a while, I'll put some empty place. I'll choose what to write down here later. So, but remember, we can do it as large as we want, right? So, because of unboundedness of f, we can choose psi k in that interval such that this will be as large as we want, right? And remember, I want to make integral sum as large as we want. So integral sum should be very, very large. Okay? So I should estimate integral sum from below, which is sum of those quantities. Okay, so I will write like that. F of psi k times delta xk plus sum I from 1 to n f of psi I delta xi, I not equals to k, right? That is precisely f of psi k delta xk plus s tilde f p psi. Now, I want to make it as large as we want, let's say greater than arbitrary chosen, okay, doesn't matter. So, give me arbitrary constant a, right? So, I take arbitrary constant a in R, right? And I want to make this greater than a. How to guarantee it? I can guarantee it if, okay, what is it? F of psi k should be greater than, let me write it down, a minus s tilde f p psi over delta xk. Yeah? So, once again, look. I want to make integral sum as large as we want. If we can do it, then for sure there is no limit of integral sums, right? Because we need to prove that integral sums can be different from arbitrary I sufficiently large, right? And we'll prove even more that integral sums will be as large as we want. How? So I want to have this inequality, and now look how we consider this set of p and psi I, so on, right? So you see, take arbitrary set of points x, right? Then choose arbitrarily psi I on intervals xi minus 1 xi, except for I equals to k, right? So all other choose arbitrary, doesn't matter. But once we choose p, we choose psi I, right? Then I choose psi k in such a way that f of psi k is greater than this number, right? So look, take arbitrary p, arbitrary points psi except for psi k, right? This is not chosen yet. And this psi k is not here, right? So it's okay. S tilde doesn't depend on psi k. Delta xk also is fixed now, right? And we can find psi k such that this inequality holds. And once this inequality holds, it automatically implies that our integral sum is sufficiently large. It means there is no limit of integral sums. They can be as large as we want. So theorem is proved. No limit of integral sum if f is unbounded. Okay. So Now, I need to make an extra section which is not in your lecture notes, but I need it. Why? Because of some things which I don't want to consider. So, to be able to follow Zorich's textbook, we need to learn more about limit over base. Limit over base, that is a notion, okay, it is useful also, but I would prefer to consider Darboux sums in more details. In Zorich's textbook, Darboux sums, they are considered also, but I would say what I want to give now, you can find in exercises of Zorich's textbook. So, now next section, I would say, is a solution of one exercise of Zorich's textbook. So, and let me call it Darboux integral. That is another concept, and it turns out that it coincides with Riemann integral, but that is not so easy. We proved f of psi k can be as large as we want, not the sum of integrals, but that is what was written. So f of psi k is as large as we want, and it implies automatically integral sum is greater than a. What was written? That is. Is it clear? So, the integral for f of psi k implies the inequality for integral sum. So, Darboux integral. Okay. Look, this theorem says that if we want to consider Riemann integral, then the function should be bounded. So, for next section, I'll suppose it from the beginning. So, suppose f is bounded on AB. So, from the beginning, we suppose that the function is bounded. You know that it's natural supposition for Riemann integration because of this necessary condition. So, we don't need to consider unbounded functions. Then once again, we consider arbitrary partition. So, let me draw the picture once again. AB, somewhere we have a non-negative function, y equals to f of x, and we take once again a partition. So, P partition. partition. Now we construct different types of sums. Why it's different? Because for Riemann integral sums, we should choose arbitrary points on each of small intervals of our partition, right? So we split our interval into small pieces, and then we choose arbitrarily psi on this small piece. Now we consider the following numbers. Mi, capital Mi, is supremum f of x for x in interval xi minus 1 xi, 1 up to n, and little mi's infimums. Again, I from 1 up to n. Those numbers exist. Why? Because our function is bounded, right? Hence, both supremums and infimums exist. So, those numbers exist and they are finite. Now, what we do? We consider open Darboux sums. These are u of p f equals to the sum capital Mi delta xi, upper Darboux sums, and lower Darboux sums. They are L of P f equals to sum I from 1 to n, little mi delta xi. So, upper and lower Darboux sums. What is their geometric meaning? In fact, I would say, from my point of view, they are better suitable to understand what is area. Why? Because look, what are lower Darboux sums? We take arbitrary interval, small interval, right, of our partition. Look, then we look for all values of our function over this interval, and we take infimum somewhere here, right? The smallest, roughly speaking. Of course, it might be minimum, but in general need not to exist. I mean, infimum always exists, but minimum not necessarily, right? It does exist for continuous functions, but we don't suppose now the function is continuous. So, I do the same for each of those small intervals, right? So, these are little mi's. So, let's say here x3, right? And this is m3. This value is m3. Infimum over x2, x3. And then, like for integral sums, what is lower Darboux sum? Is the area under this piecewise constant function, right? So this area is precisely L of PF, lower Darboux sum. Analogously, what are upper Darboux sum? We should take supremums. So it gives those values and you see that now what is an advantage from geometric intuition? You remember when we considered integral sums, right? What it was? It was an area of some figure which approximates our trapezoidal figure. But what means approximates? In which sense? Just some not clear considerations may be used, but here everything is very clear. Look, what is for our figure, trapezoidal figure? For sure, this is between lower figure, right, and upper. So we have, once we take a partition, right, and we construct lower and upper sums, they are areas of two figures. One of them is contained in our trapezoidal, and another contains our trapezoidal figure, right? So our area is between them. It means that it is essentially better to explain what means approximate. If we can do in such a way that the difference between those two larger and smaller figures is as small as we want, right? Then it means there exists an area of our figure. That is suitable definition of what is area. That is quite different from much less accurate than the Riemann integration. Much less accurate. What means much less accurate? Not much less accurate, I would say. In fact, look, this supremum means that we can approximate capital MI as we want by values of f, right, over this interval. It means Riemann integral sums can be very close to lower double sums or to upper double sums, right? So it depends on the choice of psi I. For suitable psi I, they will be extremely small, extremely close to either upper double sums or lower double sums, right? So why they are less accurate? No. Just a minute. Why is the main difference about these two integral? It's too early to answer. Okay, let me continue. So, for a while we have Darboux sums. Now, look what happens. Let me study in more details properties of those Darboux sums. What I mean? Look, let me give a definition. A partition P star is a refinement of the partition P if P star contains P. So what means refinement? We add extra points of the partition, right? So it means if we had such a partition, what means refinement? We take extra points of partition somewhere inside our intervals, right? We add some points. That is refinement. And that is very suitable. Why? Because now let me formulate a lemma, which is property of Darboux sums. So, if P star is a refinement of P, then upper sum of P star is less or equal than U of Pf, and lower sum is greater or equal than lower sum of the partition before refinement. So, look, once we add points, then upper sums will be smaller, lower sums will be larger. And in fact, it means once we add points, we obtain better approximation of our area, right? From geometrical point of view, it means they are better, right? Now let me prove it. So refinement means that we add points. And we can add points one by one. One point, then other point, and so on. So it's sufficient proof. It is sufficient to prove lemma for P star equals to P together with just one point, X star, let's say. So, what it means? I add just one point somewhere, like here, right? X star. Somewhere in between, in one interval, I add one point. Why it is sufficient? Because arbitrary refinement, we add more points, right? If adding one point we have this property, then we continue, apply more and more, and definitely we have this point for arbitrary refinement. Okay, let's have a break. So, take where is X star? Yeah, I didn't choose yet. And let us choose X star to be somewhere on, let's say, xk minus 1 xk. So, look, we have xk minus 1 xk, right? Other points are somewhere, I don't care about them, right? So we had our partition. Let me recall. Partition is a set of points of our interval AB. And then refinement means that we add points. I don't understand what means question, how can I explain what means to add points? Do you understand what means to add points? So I have points and I add some more points. How to explain? For example, here, right? We had points, right? And I add one point, let's say here, X star, right? So I add the point. Now, what is about our function? Okay, it is somewhere there, right? Like that. That was our function, let's say, y equals to f of x. Now, u of pf is a sum. And there is a term of this form. So, u of pf is a sum of such terms, right? So, what means capital MK? We take supremum over this interval, here it is, that is MK, right? That is MK. Supremum of our function over this interval. And we multiply it by the length of this interval. It means this term is precisely area of this rectangle. Area of this rectangle. Okay? Then, look. We add the point. So what is u of p star f? All other terms will be the same, right? Because we didn't touch other parts of our partition. So all other terms will be the same as we had before. Now, some new terms appeared. Okay, how to denote them? Let's say m tilde 1 times x star minus xk minus 1 plus m tilde 2 xk minus x star. Other terms are the same. So once again, look, we had one term, capital Nk times the length. That is area of this rectangle, right? I add one point to our partition. What it means? So now instead of this one interval, I should consider two intervals, right? So, two terms appear in upper Darboux sum. Which terms? One of them we take, let's say, where is supremum over this interval? That one, right? And that will be m1 tilde, this supremum over the interval xk minus 1 x star. Another is the same as mk, right? Now look, so what is new upper sum? Instead of one interval, we have now two intervals. And we multiply supremum over one of those intervals times length of the first part, and supremum over the second part times the length of this part, right? So what is the sum of those two terms? It will be the sum of areas of two rectangles now, right? That one plus this one. So, let me compare them. We had this term, area of the large rectangle, right? And we replace this term by the sum of two. That one plus this one. Definitely, this result, this summation, will be less or equal than the area of the large, right? Because we took supremum over a small interval, right? So here it is strictly less than. Definitely it cannot be larger, right? Because it's supremum over a smaller interval. So, other terms are the same, right? And the sum of those two new terms is less or equal than that one term. It means we have the desired inequality, right? That's the end of the proof. And very nice corollary. For arbitrary two partitions P1, P2, L of P1 F less or equal than U of P2 F. So, arbitrary two partitions, right? Take arbitrary two partitions. Lower sum is less or equal than upper sum. That is not obvious, right? Because absolutely different partitions, right? So we take infimums, maybe infimum somewhere can be, look, for example, here, infimum over this interval coincides with supremum over that interval, right? So different lower sums, nobody knows, right? But nevertheless, it turns out this inequality holds. Why? Proof. Consider P equals to P1 together with P2. So it means we take all those points together, right? So every point of partition P1 and together with all points which are in partition P2. P is a refinement of both P1 and P2 simultaneously, right? Because we add some points of P1 to obtain P, and we add some points of P2 to P1 to obtain P. So P is a refinement. Then what we can write? That is just a consequence of our lemma. Look. Then L of P1F less or equal, look, so P is a refinement. For refinements, look, P star is a refinement, lower sums are larger. So less or equal L of PF. Of course, for one partition, right? Lower sum is less or equal than upper sum. It's obvious, right? Because infimums less or equal than supremums, right? For sure. So that is less or equal than U of PF, right? And then, again, we use this property, right? P is a refinement of P2, so less or equal U of P2F. And that's all. That's it. Corollary is proved. And that is very important corollary. So look. So look, what? Now this block is over about properties of Darboux sums, and let me continue with definitions. So next definition upper Darboux integral of f over ab is I with upper line, right? I bar, if you want, I star of f equals to infimum over all partitions of upper Darboux sums. So we consider all upper Darboux sums and take their infimum over all possible partitions. That is upper Darboux integral. Analogously, lower Darboux integral of f over AB is I underlined of f equals to supremum over all partitions of lower Darboux sums. And corollary which we proved implies what? For arbitrary f bounded, of course, right? Bounded. I star exists, I underlined exists, and less or equal than I overlined. Right? Why? Because every term, every member of the set of all lower sums is less or equal than every term of the set of upper sums. So then definitely infimum is greater or equal than this supremum. And of course, what is most important for us is the case when they are equal, right? If they are equal, then let us call it Darboux integrable function. So definition. Definition. F is called Darboux integrable if I overlined equals to I underlined of F. Their common value is called the Darboux integral of F. I of F, let it be. Just I of F, without overlined or underlined. And let me formulate and prove a simple theorem which is useful, very useful in fact. So, theorem 1 here, I think the only theorem in this section. Necessary and sufficient condition. Sufficient condition for Darboux integrability. F is Darboux integrable if and only if for arbitrary epsilon greater than 0, there exists a partition P such that the difference between upper and lower Darboux sums is less than epsilon. And that is once again very natural criterion which says, in fact, what is area? When a figure has an area, when? If and only if, you see, you can find two figures, one of them inside, another outside, right? One of them is inside our figure, other contains our figure. Both figures have areas because they consist of finitely many rectangles, right? So both of them for sure have areas, and the difference between those areas, which is practically what is? Practically consists of very small rectangles, right? So difference between those areas should be as small as we want. That is very natural, geometrically natural assertion about what should be understood as area, right? Because in fact that is not so easy to define what is area, and the most natural way is just to find a figure which consists of rectangles, because obviously what is area of rectangle, right? And if you can find two such figures, one of them inside, other outside, and difference between the areas is as small as you want, then you have an area. That is why Darboux sums are very suitable from geometrical point of view. I mean, if you look from physical point of view, maybe Riemann integral sums are better because they relate to, okay, some process to find antiderivative, to find primitive, right? That is slightly different way. Darboux integral, Darboux sums are more suitable for geometric meaning, for area, because you see, just by definition of what is area, the only way to define the area with the help of such figures, right? And it means that geometrical sense of Darboux integral is immediate. This is area under the graph, just by definition, right? Because what is area? The only way to define the area is by this. Okay, proof. So let's start with this part. So we suppose that f is Darboux integrable. It means overlined I equals to underlined, right? So we suppose it. We suppose. Right, then what it means? Look, I underlined is a supremum of some set of numbers. What means supremum? It means that we can approximate as close as we want, right? We find, so for arbitrary epsilon greater than 0, there exists a partition P1 such that the difference between I underlined minus this lower double sum is less than epsilon over 2. Analogously, also we can find by the definition of I overlined, we have here infimum, right? So it means we can approximate this infimum as close as we want. So U of P2F minus I overlined of F is as small as we want. Now look, for a common refinement, for the common refinement, so take P equals to P1 together with P2, common refinement of those two, P1 and P2. Then what we can write? Let me write a sequence of look, I will rewrite this. Okay. So I star of F minus epsilon over 2 strictly less than L of P1F, that is this inequality, right? This inequality I rearranged all terms. Then we use property of refinements, less or equal L of PF, right? Arbitrary lower sum less or equal than upper sum with the same partition, right? Then, by the property of refinements, upper sum is less or equal than upper sum of P2F, and the last term, U of P2F, is strictly less than I overlined plus epsilon over 2. But remember the supposition I overline coincides with I underline. So those numbers coincide. So the difference between the left-hand side, the most left-hand side, right, and the most right-hand side, what is the difference between them? Epsilon, right? The difference between the most right-hand side and the most left-hand side is epsilon. So you see, both L of PF and U of PF are inside an interval of the length epsilon. Both numbers lie inside an interval of length epsilon. Hence, difference between them is less than epsilon as well, right? So, it follows that U of PF minus L of PF, which is non-negative of course, is less than epsilon. And that is precisely what we wanted, right? That is precisely what we want. So, necessity part is done. Now sufficiency. Look, so now we have our property. So for arbitrary epsilon, we found a partition P such that the difference between upper and lower sums is less than epsilon. It's sufficiently small, right? Then, look, so we know that I underlined of f equals to supremum over all p, right? This is supremum over all. In particular, it is greater or equal than our concrete p. Not very good. Maybe here I'll use p1, let's say. Do not mix with our p, concrete p, right? So, analogously, I overline of f is infimum over all p2 u of p2 f, and it is less or equal than arbitrary concrete, in particular our u of pf. So now look what happens. Let me indicate on a real line. So here we have L of pf, right? Oh, there we have our I underlined, then I overlined. In general, I mean, I want to prove they coincide, but in general less or equal, right? And then we have u of pf. And now you see what we know. The length of this interval is less than epsilon, right? Hence, the difference between overlined f and underlined f is less than epsilon. And it is non-negative, right? Now look what we have. That is a non-negative number, and we know it is strictly less than arbitrary positive epsilon, right? Which non-negative number is less than arbitrary positive? Only 0, right? So it follows that overline f coincides with underline f. And theorem is proved completely, right? Okay, so I think the section, the section is over then. Now, maybe I have less than 10 minutes. Okay, let me give a short section. Seven point 3. Equivalence Darbu and Riemann integrals. And maybe formulation. Because definitely I'll not be able to prove. Theorem is rather complicated, in fact. So, theorem. F is, suppose F is bound on AB. Then F is Darbu integrable if and only if F is Riemann integrable. In this case, I mean, if F is integrable in any of those senses, right? It's Darbu integral coincides with Riemann integral, with its Riemann integral. So, integral a to b f of x dx equals to I of f. And in fact, one part of this assertion is relatively easy, and I can prove it in 5 minutes. Yeah, I can do it. So, today I will be able to give a part from Riemann integrability. So, proof Riemann integrability implies Darbu integrability. So, we suppose the function is Riemann integrable. Those integrals can be used in many cases. About the question where they can be used. But to compute those integrals, you need only to be able to find indefinite integrals. That's another story. Okay, so what we know, we suppose there is an integral, right? Equals to the limit as norm of the partition tends to 0 of integral sums. So it exists. Suppose. So take arbitrary epsilon greater than 0, right? And what we know then? We know there exists delta greater than 0, such that for arbitrary partition P with norm less than delta, and for arbitrary choice of points psi I in between, we have the difference less than epsilon. In particular, it follows that I can write inequality of this form, which is, let me write down, f of psi I delta xi less than integral f of x dx plus epsilon. Now look, psi I here arbitrary in between. So it means I can take supremum of xi between xi minus 1 and xi. So this inequality implies I can take supremum of xi's, and it is also is valid. So sum of supremums for psi I between xi minus 1 and xi, f of psi I, is valid as well. Because if it is valid for arbitrary psi I, then it is valid for supremum. And that is less or equal, of course. Supremum may take inequality not strict. And that is precisely u of pf. Analogously, we prove inequality f of x dx minus epsilon. Now look, difference between those two, then less than 2 epsilon, right? Because we see integral minus epsilon, L, U, integral plus epsilon. So difference between upper and lower sum is less than 2 epsilon. And then by necessary and sufficient condition we have, so u of pf minus L of pf less than 2 epsilon, hence f is Darboux integrable. Moreover, Darboux integral is somewhere between them, right? Darboux integral. So it means Darboux integral differs from Riemann integral less than epsilon. And then once again, epsilon is arbitrary, hence integrals coincide. So one part is proved, that is an easy part. Okay, let's finish now.